Hello YouTube! Today we are going to talk about multidimensional throwing, and it's actually quite interesting because it's quite easy if you compare to our last video where we talked about throwing in one dimension, and multidimensional throwing is really not much more. What do we have when we have multidimensional throwing? Well, we have some kind of parabola our object travels on, and that's really all there is actually. The one big thing about every throw is that the acceleration is supposed to be constant and going in one direction, and that's basically it. The acceleration is constant in one direction and everything else is a special case. Now we know the formula for a constant acceleration. Let's look at it again. And we get y of t is equal to minus 1/2 gt squared plus v0 in y direction times t plus y0. And we get y dot, or the derivative of y with respect to time, both are the same, is equal to minus gt plus v0 in y direction. Now it's quite interesting that I now chose the y direction. Why did I choose y of t and not x of t? Well, it's pretty simple, because now I just said, oh, my up direction should be the y direction and my direction to the right should be my x direction. I could have called it ape of t and said, oh, ape is my height, or I could have called it hubuku, and hubuku of t is going to be my height, and would have all been the same. So it's not about the letter that's right here, it's about what it actually represents, and in this case it's the height that it represents. Now there's another coordinate that we should look at, which is the x coordinate. There's not only the y coordinate but also the x coordinate in a multidimensional throw, because the least amount of dimensions you have when you have multiple dimensions is 2, obviously. Now adding other dimensions to that formula will be really easy, so we are going to look at the simplest of them all, and then we are later going to add more dimensions to it. So what other dimension do we have? Well, we have the x dimension, and now comes the interesting part. Now let's look at the formula for the x dimension, and you're going to see the x dimension formula is actually just v0 in x direction plus times t plus x0. So the velocity in the x direction is actually constantly the v0 in the x direction. Now this is the interesting part. This is the important part. This is the part we should always remember, because it's the independence of the spatial dimensions. X and t are completely and utterly independent. We can only artificially create some kind of interdependence when we solve x of t for t, and we get t of x, and then we put it in there, then we get y of x. But otherwise they're completely independent. If we move in some way in the x dimension, that has nothing to do, literally nothing to do, with how we move in the y dimension. That's completely cool. One of those awesome things in physics. So we talk about the superposition of spatial dimensions, because one movement can be in superposition with another movement. If you move to the right and you move upwards, you can actually separate those movements. If you move diagonally to the moon, you can separate it in a direction that goes to the right, and a direction that goes up, and a direction that goes forward. You can separate every single movement that you can describe. Every single one you can separate into our three-dimensional space. So 3 single dimensions, 3 single movements. So when you have, for example, some kind of force and it goes in one direction, you can actually separate the force into all its spatial components. In the x component, in the y component, or in the component that goes parallel to something, in a component that goes perpendicular to something, and we're going to talk about that, and we are going to use that so often that we really had to talk about this right now, that we talk about the superposition of spatial dimensions, because it's actually quite important, even if you don't realize it. And it doesn't matter if you know the name, or you know kind of what it means. That's not the important part. Don't remember x and t are independent. Remember that you can separate things. if something relies on spatial orientation, you can always, always, always separate it into its components. And it doesn't matter what components. You can choose the components that go parallel to something. You can choose the components that go in our x, y, and z direction. You can choose components that go perpendicular. You can choose which components you want. That's another thing of space. It's homogeneity and isotropy of the space, but those words don't matter. It matters that you understand what it means. You can separate everything that has something to do with space into its components. And it doesn't matter what base you use. You can use a parallel, orthogonal base. You can use a base of the XYZ components. It doesn't matter. And that's the interesting part. Best part. Don't worry if you have no idea what it means, even by now. We are going to talk about that in a video about forces and how to separate forces into their components. So don't worry, we're going to talk about that some more. Now let's look at the examples, because just having some x and t is very boring. Let's look at some examples. First of all, let's look at the drawing of it. That's our first example. The drawing of it is very basic. We basically only have the y component in this direction. This is our y direction, and to the right we have our x direction. And basically something is moving constantly with v0 in x direction times t to the right, starting with x0, and it's moving upwards with, and this is the interesting part, with a v0 y component times t and a minus 1/2 gt squared component. And we can actually, because they're just added, like here, there's a plus between them. Here, there's a plus because they're added. That's linear, so they are just added. So we can actually describe them as three separate functions that we all just add together. The y0 function, the y0 in y direction times t function, and the minus 1/2 gt squared function we just add onto that light blue function here. That's nice and all, and I wanted to at least show it to you sometimes, but I have something far more interesting, because now I'm going to talk about with you how to calculate, for example, the height of this, or the height of this, I should say, and the distance that we can travel. Let's start with the height, or the height. The height we get by taking the time and substituting it in some kind of formula to get the height. Once again, we go by condition, time, height. In the last videos, we always went from condition to time, for example, to braking distance, or from condition to time to some other distance, from condition to time to something else. And that's what we do here again. We take the condition, we go to the time, and now we get the height. Or we take the condition, go to the time, and get the width. And it's basically always the same way, at least for most mechanical problems, because most mechanical problems rely on some function that depends on t. If the function doesn't depend on t anymore, we solve for that variable. For example, if we have a w of phi, or our Winkel phi, then we take the condition, then get the phi, and then do something with the phi. Let's start with the height. The height we get by simply taking the condition that our derivative of the height function is 0. Why do we do that? Well, it's pretty simple. It's mathematics. Because mathematics tells us that at the highest point, you're actually not moving upwards or downwards. At this point right here, you're not moving upwards or downwards. You're actually just moving to the right. At this point, you're clearly moving downwards. At this point, you're moving clearly upwards, but at this point, you're actually not moving upwards or downwards, just to the right. So the derivative of our height function, which is how much you go up or down at some point, is just going to be 0. So we take that and we substitute our formula for y dot of t, or the derivative of y with respect to t of t, and just solve for t. Right here, and we get some time out of there. That's v0 in the y direction over g, and that's nice and all, but let's substitute it into our formula for our height. So we substitute it there and we get this whole thing, And this is the total height we can reach at maximum. If you want the relative height relative to y0, you actually get just the front part of this. Now there's really not much to talk about other than maybe calculating some example or something, but it's actually just this formula. There's not much to it actually. We should remember anyway that this is our condition, and then we solve for the time, and then we substitute the time into the y function. So for our width or our maximum distance, we actually have another condition, which is that we land on the ground, which is that our y is equal to y0. So we land on the ground, so that's our formula for the height once again. Just substitute it and calculate it. And if we now take our width, we get this condition, and we substitute it, and we calculate a bit, and we get this following equation. And now from that we can also get the time. It's a bit more difficult because we don't have this easy equation, this easy linear equation, but we have a bit more difficult equation like this. But we can actually factor out the t, because here in this part is a t and in this part is also a t. So we can factor out the t, write it in front here, and have this huge bracket. So either this is going to be 0 or this is going to be 0, so that the total is going to be 0. So we either have t is equal to 0 or we have t is equal to this kind of stuff. So once again we get 2 results, even though we expected just 1 result. Well, this is a problem. Once again, it's our mathematical description, and I would really advise you to get 2 results, because otherwise you have calculated nonsense, because the actual thing we throw has been on the ground at 2 points, because when you throw it, it's actually on the ground. You start on the ground. So if it would start up in the air, that would be total nonsense. So of course you get 2 times. One time where you actually started on the ground, and the other time when it actually lands on the ground once again. So that are those 2 times. And we know that the time of 0 is not the time we want the other time. So we actually just take the other time, which is this one, and we substitute it. And now pay a little bit attention, we substitute it into the x coordinate, because we don't want the height of the whole thing after the time it needed to fall down. We want to get the width, or we want to get the distance, I should say. So we should get the distance of this time, and this is going to be the total distance we traveled. And this is a nice formula, and we get this. This is a width, basically. And if we want to get the relative width, we take only the front part once again. And that's a nice and wonderful formula about the width. So we've calculated the height by h equals to minus v0 y squared over 2g plus y0, and we've calculated the maximum distance by 2v0 in y times v0 in x over g plus x0. That's 2 simple equations, and we don't really care actually. Those equations, we don't really care. We don't remember them. It doesn't matter. What we do want to remember is how we get there actually. How did we get there? We got here by taking the condition, which was here, the derivative of the height function is 0, and then we got the time and substituted the time. And with the width, this was the total width is going to be the y0 once again, or 0, it doesn't matter. And then you substitute it, you got the time, and then you substitute the time into here. So it's always going to be condition, time, and substitution. That's our usual work. And that's really important to remember that instead of the formulas that come out at the end. You can create the formulas every single time you need them if you remember how you actually got them. Because everything in between is just math. It doesn't matter. The physics behind it is remembering how you actually got there. How did you get there? You got there by having your condition, solving for time, and then substituting for time. You got here by having your condition, solving for time, substituting your time. And that's basically for every function of the time you actually have. Now we're going to see right now that there can be a function that does not depend on time. And that's what we get right down here. Because right down here we substitute something very interesting. We substitute sine of theta times v and cosine of v times v. So sine of v times v and cosine of phi times v. So why do we do that? Well, I've created this ultra triangle of awesomeness for you, which is just, we see the velocity vector, and the velocity vector actually is made up of two components. And once again, this is using the superposition of our spatial dimensions, which is just that they are independent of each other. So the v0x component has nothing to do with the v0 and y component. There's really nothing to do. They're completely two separate things. Now to get them, we simply use this triangle. We have a right angle right here, and we have a angle phi here, and we just see, oh, here, this is the opposite leg, and this is the hypotenuse. So we divide the opposite leg by the hypotenuse and get the phi, and then we can solve that for our actual v0 and y direction. And we can do the exact same steps for our actual adjacent leg, which is v0 in the x coordinate, by just taking the exact same steps, just with the cosine instead of the sine. Now let's resume to this formula right here, which is just the upper formula, this one, substituted with our cosine and sine definitions of the velocity. Because what do we have here? Right here we get a really interesting part. This w is actually dependent on the angle and on nothing else, or on the angle and the velocity, but we are going to assume that the length of the initial velocity is always going to be the same. So we have a function of the angle actually, and our same thing as every year, James. We use our condition, which is going to be that the derivative of it is going to be 0, and then we solve for the angle, and then we have the angle. In this case we don't need to substitute because we don't want to know anything further, but we could substitute it to get, for example, the maximum width. Or let's just do that afterwards. Let's just do that. So we are going to once again take the condition, solve for a variable, and then substitute that variable. That's what we do every single time. So right now we have the width as a function of our angle in which we shoot our thing, our ball or our golf ball or whatever we shoot. And now we want to know the maximum width. At what angle do we have the maximum width? How do we get the furthest? And we know that by once again taking the derivative and setting it equal to 0, because the maximum of something is always the derivative equal to 0. That's almost the definition of a maximum. Almost. So let's just do that. Let's just do that. And we do that and we get this bunch of crap here. What did we do there? We actually used the product formula, or as many of you will know it as the product rule of derivative or derivation. The product rule. So what do we do with the product rule? Where we derive the first thing and then multiply it with the second thing underived, and then we derive the second thing and multiply it with the first thing underived. So the first thing derived is cosine, then we have cosine times cosine, which is cosine squared. And then we derive the second thing, which is minus sine, so get minus and then sine squared. So we have cosine squared minus sine squared. And that's quite interesting. So if we want the whole thing to be 0, then either this has to be 0 or this has to be 0. These are just some constants, for example 15. So 15 can't really be 0. So this right here isn't really 0, but this can be 0. If cosine squared of this angle is equal to sine of squared of this angle. So if we would be very much physicists and we already knew all of that, we could actually derive that the angle is going to be 45 degrees. But we are not that good. Because why on hell would sine and cosine be equal at 45 degrees? We don't know that yet. So let's just assume we don't know that. But there's actually a small little trick we can do to derive that. We can actually get that by saying this formula right here. If we know this formula, we can actually get to this result. How do we get that? Well, we use this formula and solve for cosine squared. Cosine squared is nothing else than 1 minus sine squared, so we can substitute it right here. So we have sine squared is 1 minus sine squared. Then we can solve for sine, and sine is equal to the square root of 1/2. So our angle actually has to be the arcsine of the square root of 1/2, which is about 45 degrees or pi/4, depending on how you set up your calculator. So by having this information about our angle, we can actually calculate what our maximum distance is. If we just substitute this angle right here, and sine of this angle is going to be 1 over the square root of 2, and I can already tell you cosine is going to be the same. So we actually have, as a formula for our maximum angle, we actually have 1 over the square root of 2 times 1 over the square root of 2, which is just 1/2. 1/2 times 2, that cancel out, and we get v squared over g plus x0 for our optimal angle. So if we use the optimal angle, our maximum distance is given by this formula right here. So in the last part of this video, we're actually going to talk about how do we do that for multiple dimensions. First of all, we just want to quickly introduce the so-called trajectory, which is in this case a trajectory parabola. How do we get that? Well, we simply solve our x of t equals to v x times t for the t, then we get some t, and this we substitute into the y of t, because then we get a function y of x, which is just minus 1/2 g times x over vx squared plus vy times x over vx and plus this y0. That's quite interesting, but also admittedly quite boring. Why is it a parabola? Well, it actually has an x squared here, or x here, and no x there. So it's actually in the form of a times x squared plus b times x plus c. So that's the normal form of a parabola. So now let's talk about the vectors. And here we see how we do the whole stuff with vectors. So we have the x-coordinate, which is just v0 x times t plus x0. And what we did here is we factored out the t squared out of all the spatial coordinates. You could have written the t squared into each and every spatial coordinate right here, but that's quite repetitive, so we didn't do that. It would have been boring. And we didn't do it here either. We didn't write t into each spatial coordinate, because there would have been quite some work. So by writing them as a vector, we can actually factor out some values like t squared. That's great and all, but isn't it more writing? Like, I have to do these strange brackets and everything, and it's not so obvious anymore. And then comes the next part. In the next part, we actually write the x, y, and z vector just as the x vector, our position vector. Our position vector is then equals to something. And this something is this first vector times t squared, and we can call the first vector a vector or the acceleration vector, but we don't need to. And then we have the second vector, in which only the initial velocities of each spatial dimension is. So we can actually say it's just the initial velocity vector. And here we only have the each individual initial condition for our spatial orientations, or initial condition for each and every coordinate. So right here we can also substitute just one small vector, which is just the initial coordinate vector. So we have our spatial vector is just equal to our acceleration vector times t squared plus our initial velocity vector times t plus our initial spatial orientation vector. And we can also derive that, and we can also get each and every formula that we had before derived very simply. We just derive that and we get this kind of crap here. And there's only one big difference by switching from 2 to 3 dimensions here. The only difference is that we calculate our width with another way. So the maximum distance is actually calculated by using the x maximum distance squaring it plus the y plus the z maximum distance squared, and then taking the square root of that, because that's just Pythagoras. The Pythagorean theorem says that v squared is equal to vx squared plus vz squared, or vy squared I should say, and that's simply saying our maximum distance is just the square root of the two spatial distances combined. So how do we get that? Well, we simply take the exactly same calculations and use it for our width in the x direction, and when we take it for our width in the z direction, and then we get our total width by this simple formula, which is just Pythagoras. So basically we have the same calculations. And in the next videos we're going to look at the unit, or in the later video we are going to look at the unit vectors ex and ey and e0, and we're going to look at how they work and how multiplying some has a special result. But first we want to be talking about forces, so may the force be with you. Right now though, let's just recapitalize on what we learned today. Number one, and the big number, is the independence of spatial coordinates, and that's called the superposition of spatial dimensions, which is quite important. So whatever we do in our x coordinate doesn't matter for our y coordinate, whatever we do in our y coordinate doesn't matter for our z coordinate, and so on. The second thing is that we remember this easy formula, which applies to about 99% of physics, that we first use the condition to get onto the variable, and then we use the variable to substitute it and to get our result. Of course, it's not always going to be that easy, and in the special cases I'm going to talk about it a bit more, so you have the idea, I guess. The third thing is that we actually remember what conditions we had for the height. So for the height we have that our y, the derivative of y respect to t is equal to 0. And our fourth thing is that we know what we have for the maximum distance, which is just that our y of t is equal to y0 once again. And we substitute that into the x and not the y coordinate, because otherwise you're just going to get 0. And the fifth thing we talked about was how to get the maximum distance depending on the angle. The best angle is 45 degrees. And the last, or the sixth thing we talked about was the parabola, and the last thing were the vectors.